the lens. The second aberration of the Seidel aberrations, and that's what these third-order aberrations are called, is Coma. And essentially what that means is that spots on the focus will make nice round, or spots on the optic axis, excuse me, make nice round dots. But as you get to sources and point sources that are off the optical axis, as the image size increases, they don't make nice round dots anymore, but they make these sort of comet-shaped or comma-shaped things. And that's the name where the name Coma is taken from. Again, if we look at a perfect image here, we see a nice round dot. That's the best we can do. If you insert Coma into a system, you go from sort of a nice round dot and almost a wedge-shaped dot, with the brightest area of the dot being right there. This aberration is proportional to r squared and h sub I squared, so it gets worse both as your lens size increases and as the size of the image increases. Another one very similar to Coma is called astigmatism. In astigmatism, spots turn into lines. Again, this is proportional to r squared h sub I squared, so it's important for large images and lens sizes. Perfect aberration, or excuse me, a perfect imaging system is going to create a nice round dot here, but with astigmatism, your round dot turns into a line. This is badly astigmatized or astigmated image right here. One of the most difficult ones to understand is field curvature, where the image plane is not a flat surface. And so what we're going to do here is I'm going to cut into a video, and you may not be able to see all of it because of the limitations of the video medium, but I hope you get most of it across on the definition of field curvature.
So let's take a look and see if we can really understand this idea of field curvature using an optics lab simulation. Here I have a simple point source, a lens, and my observation screen sitting at the focus of the lens. If I go ahead, and I'm just going to go ahead and turn on a low-res extended source and see what happens, we can see that near the center of the image, for the rays that come near the center of the lens, the focus doesn't seem to shift much. But if we look at the circle of least confusion for other rays, it looks like the circle of least confusion might be right here for those rays that are further away toward the image. And in fact, it almost looks like there's a curved region right here where the spots are at the best focus. If we go ahead and look down here at the image, you can see that we have a very nice cluster of rays near the middle of the image, but the blurriness of the image, or the pattern of the rays, gets worse and worse as we go out. And in fact, if we do have a curved image plane, these should become more closely grouped as I slide this over. So let's see if that actually happens. So I'm going to go ahead and move my image plane here, and look what's happening. In the center they're getting a little worse, but they're getting better out here. If I move my image plane a little bit further, if I can go ahead and grab this, come on you. There we go. And we are improving things out here as we move the image plane. Okay, and so from here we can go ahead and actually get a measurement of this idea of field curvature, the fact that there seems to be a curved plane a couple millimeters in size where the rays focus a little bit more. If I go up to the mode, and you can't see it on here, but if I go up to the mode command on the optics lab title and click on measure curvature, I come up with a dialog box. I'll click OK, and I don't see anything yet because I have to take my source out of low-res extended source mode, and then all of a sudden I get a graph that looks like this. Here we have a spacing on the optical axis in terms of millimeters. This is horizontal spacing and this is vertical spacing, and this is the curve of the ideal best focal plane. In fact, the focal plane is not a plane, it's actually a curved surface, and in reality this is going to look like a cup. So field curvature just corresponds to the idea, and let's go back and look at this one more time. Field curvature simply corresponds to the idea that the image plane in fact is curved rather than a perfect plane when you have aberrations in your system.
Finally, the last one, the fifth one, is distortion. And in distortion, the images are bowed at the imaging plane. This one is proportional to the image size cubed times the radius of lens. So really it becomes very important for very large images or large fields of view. And you see what should be a square grid of points here actually has a shape that looks kind of like this. It's bowed in at the edges. And this is called pincushion distortion, and is one of the two types of distortion we see. but it essentially takes what should be rectangular or square images and turns them into images that have bowed sides. And those are the 5 different types of aberrations, and gives you a sense of, if you see one, what you can attribute it to and how it depends on the polynomial equation we saw.